All right, we're at 9 o'clock Seattle time. So thank you for people who have come. And it seemed like this would be a good idea to get faculty and postdocs and students together and have a forum for us to give just short talks to each other on whatever interests us in X-ray spectroscopy, and just stay in touch and give our students some new things to read. You can please share the schedule with others. That's that first tiny URL link, and that won't let them edit, but let them see what's scheduled and hopefully find the posts to the recorded lectures. You can also email me or go to that second link, the one that has the global XAS edit, and to schedule yourself in to give a talk. It'd be particularly awesome if someone said, you know, I can give a talk, and I know two friends who can give a talk, or postdocs on something similar, and took the lead for going ahead and scheduling a thematic week of 2 or 3 or 4 talks. Beamlines, it'd be great to hear about 4 new beamlines in X-ray spectroscopy, catalyst studies, rad materials theory, whatever works. The target here is talks of about 25 minutes length if there was no interruptions. And I've asked Simo to be the designated questioner. And so if you move your mouse around a little bit in Zoom, you should see there's a little tab called chat, or a little option called chat, I think down at the bottom. I'm watching to see if Neil found it. Good, okay, all right. So when you have a question or a comment, go ahead and type it in there, and Simo will be watching those, and there'll be a couple points where I'll stop and ask for questions, and Simo can either call on someone at that point and you can unmute your mic, or he'll try to paraphrase your question. That's the plan. Simo, you there? Uh-oh.
I am here. Hello. Hi, Jerry. Hi, world. Hello, world.
Hello, world.
How are you?
Excellent. Okay.
Great.
All right.
Perfect.
So yeah, at a couple natural breakpoints, I'll stop and ask Simo to summarize questions or hand off to an appropriate party. So with that being said, why don't I go ahead and get started? So I'm going to talk about what is X-ray Raman scattering and what did Raman have to do with it. So the outline has 3 pieces. I'll give a little bit of background on what is X-ray Raman scattering, often called non-resonant inelastic X-ray scattering, or NICS, or sometimes NRIXS. And after that background, I'll give a case study on this inelastic scattering from nitrogen gas, which had the interesting result that the inelastic scattering from electrons and the inelastic scattering from X-rays disagreed, even though in the simplest theoretical treatment they ought to have agreed. And then I'll end with a little bit of history where there's certainly still gaps that maybe other people can help fill in about the relationship between Raman and Compton, both in terms of scattering physics and also as people who were contemporaries in a very similar field. All right, so you know, this is today's experiment. There's a photon in and a photon out, and we need to concern ourselves both with conservation of energy and also with conservation of momentum. When this is done with X-rays, there's many different flavors of inelastic X-ray scattering that largely separate based on the energy transfer. So you can take the very slow fluctuations that you see in photon correlation spectroscopy and convert that to an energy and say that it's 10 to the minus 10 EVs or less. Nuclear resonant IXS would be 10 to the minus 1 to 10 to the minus 4 EVs. Of course, you see phonons in a slightly higher energy range, and then plasmons and valence excitations in the sort of 1 EV to maybe 20 or 30 EV range. The core shell excitations, which are most often what seems to get called X-ray Raman scattering these days, of course, are more in the a couple tens of EVs out to 1,000 EVs or beyond. In that same energy range, there's RIX is done, of course, and at lower energies, RIX is done, is very important for electron correlations. And at higher energy transfers is where you would be trying to do, for example, Compton in the impulse limit to learn about momentum distribution functions. And inelastic X-ray scattering plays a major role in the third generation and the upgraded third generation light sources, and of course at the XFELs also. So, what do you get? What you find is the probability for the inelastic scattering event, excuse me, can be written with Fermi's golden rule in the usual way. And with a bit of work, what you'll find then is you have a cross section that separates into two pieces. So I should say a double differential cross section that separates into two pieces. And one of them is the Thomson cross section, which is just the usual polarization dependence that you get even for elastic scatter. And then the other part is the dynamic structure factor. And that has our interesting matrix element in it, which we'll be talking about a lot. And those of you who do XAS, you look at this and say, well, this is familiar, but not quite what you're used to, right? What you'd be used to for the operator here would be polarization dotted into R. And instead here we have a full e to the I q dot R. So if you're in a limit of small enough q so that q dotted into R over the spatial extent of your initial and final states is small, then you can make the approximation e to the I q dot R is roughly 1 plus IQR. The 1 is going to drop out because of orthogonality between the initial and final state. And then, again, you're going to get just an R in here as the relevant operator. And so things should look an awful lot like photon absorption, except this delta function is different, right? In XAFs, this delta function for energy conservation would be leading you right away to actually the delta function is not that different. It is still, yeah, okay, the delta function is awfully similar, but the important thing here is that this operator is different in the non-resonant inelastic scattering. Anyway, in the low Q limit, what you get here is a bulk sensitive alternative to soft X-ray XAFs or EELs. And again, you've got basically the same matrix element as Q dependence EELs, but we're going to see that there's a different, should be Rutherford cross section, pardon me. It strongly favors IXS at high Q. We'll get to that in a few more slides. All right, however, if instead you do a large scattering angle experiment or sufficiently large, then this is going to break down. This small momentum transfer issue is going to break down. And what we'll see is that when you do an expansion of this exponential in terms of Bessel functions and spherical harmonics, is that you can tune what selection rule is actually appropriate by changing the momentum transfer. So at low momentum transfer, you only have dipole transitions so that your change in orbital angular momentum has to be 1. And on the other hand, at larger momentum transfer, you get dipole forbidden transitions. So you get a relationship between the momentum transfer dependence and the final state symmetries that you can probe. The problem with this is that the cross-section is numerically extremely small. Shown here by a cartoon of, I think, 10 to the 12 incident photons, resulting in only 10 to maybe 1,000 counts per second in the X-ray Raman per a sort of relevant detector solid angle. So the need to make the experiment more feasible led to many groups developing big spectrometers. I'll show you an example in a minute. I believe this started with Kramer and Bergman with their 5 or 6 analyzer system that was used at a couple synchrotrons, especially APS. And they really were the first to raise the issue of chemical importance of X-ray Raman as an alternative to Zane's in the context of the modern synchrotrons and that as a consequence of the third generation synchrotrons, this had become something really feasible. Tim Pfister and I built Lyrics at APS. About the same time, Bergman built, what was it, a beautiful 8-analyzer spectrometer at SSRL that was enlarged by Demosthenes Sakaris some years later. Of course, ESRF has gone through a sequence of spectrometers. At the moment, it has the amazing Uber spectrometer that hopefully Simo will talk about a little bit tomorrow, or we can have maybe Christoph talk about at some future time. Petra has a spectrometer with, I think, 12 analyzers, and there are of course others. And I apologize if I left off too many of these. So this was the original Lyrics back in 2005 or so, and this is Tim Pfister. And the idea is the beam comes out of the beam pipe, it's in the plane of the spectrometer, scatters off the sample, and then each of these modules over the top has a spherically curved silicon 111 analyzer, where each one is coupled to an independent scintillation detector down here. So as we scan the monochromator, the analyzers stay fixed, and we generate an energy loss spectrum from the IXS, but with 19 different momentum transfers all at the same time. This approach of having an independent sort of 1 pixel solid state detector has been superseded by position sensitive detector based designs for many applications. And I suspect Simo may talk a little bit about that in his lecture. That being said, this spectrometer was and is a lot of fun to run. Here's data on an aluminum nitride powder. And so you can see all the different momentum transfers, and you can see the Compton gradually shift out to higher momentum transfer. Here, these features are the aluminum L23 edges. If we look here, you can kind of see there's a bump. And if you average at that bump for a while, you get the nitrogen K edge as shown up in the top right. And if you really average for a while, about 1500 volts out, you can even get the aluminum K edge in the inelastic X-ray scattering. All right, so this is where my grad students maybe shouldn't listen for a minute. We built Lyrics, and a senior professor who will go nameless here, we were talking, and they said that, I worry you've made Raman too easy. The students will graduate too fast, and you should find some really hard experiments to do. And, I was a younger professor then, so I reflected on this wisdom. And, and of course, senior faculty are always right. I know that now. And so, he was right. The students did graduate fast with a lot of papers. But that discussion, I remember, really got me thinking about finding an experiment that was impossible before we had built Lyrics, but was possible now. And that led us to the idea of doing gas phase Raman scattering. We decided to start with helium gas because there's a famous literature on double electron excitations that require new quantum numbers. And we built a little pressure cell and got really very nice data. You'll see the notation for the angular momentum involved in the transition is very complicated, with extra quantum numbers and polarity signatures and whatnot. But in any event, we could see these phonoresonances, and that was great, except we had a problem, and the problem was the experiment went too fast. We had gotten about 5 days thinking it was going to be a very hard experiment, and it took a lot less than that. So I was talking with Joe Bradley, the grad student, and we looked around and we saw there, of course, were nitrogen tanks in the hutch. And so I told him to load up the pressure cell with nitrogen gas, and I'd start doing a literature search on prior work with electron scattering on N2. And the grad student should be listening again now. And, this is why your PI always tells you to bring extra samples on beam runs, is sometimes things go faster than you expected. So that's going to bring us to today's paper. Before I get started on this exact paper, maybe I'll take a break and ask Simo, are there questions?
Yes, so actually Neil has a couple of questions. Maybe Neil would like to say them out loud.
Thanks, Simo. So yeah, I had a couple of questions, Jerry. Early on, you mentioned nuclear resonant IXS. Is that basically Mossbauer spectroscopy for chemists? Or is that?
Yeah, it's yes, at least very similar. I haven't thought about this stuff in a decade. The advantage at the synchrotron is a bit more tunability.
Mm-hmm.
I'm going to go with yes, but maybe we need to get someone to give a talk about that to actually give you a better answer. It's definitely done on a different isotope where there happens to be a good silicon or germanium reflection really close to backscatter, so that you can very, very finely monochromatize the synchrotron beam. But beyond that, I'm not remembering details right now, sorry.
Okay, I'll look it up. And then you mentioned the importance of chemical dependence of X-ray Raman scattering versus XANES. I just wondered if you had a couple of kind of killer examples to make that clear, or maybe you're going to come onto it in your talk.
Give me just a minute. I mean, the most famous example. Oh, okay. So the point of Kramer and Bergman, and they were exactly right, and this has led to a lot of the work in Raman, is that there are an awful lot of soft X-ray measurements that are just hard to do. If you're in special environments or liquid phase, you know, it's pretty hard to get it. It can be pretty hard to do spectroscopy. Right, you can't do transmission mode usually at low energies, and fluorescence mode can have really strong corrections on it. And so probably the most famous example for Raman scattering done with hard X-rays that seems to come up with different answers than the direct XANES with soft X-rays is the study on water that came out, I don't know, 10 years ago or so, maybe longer than that. And led to a lot of discussion about the correct way of thinking about the a hydrogen bond network in water.
Okay.
Certainly, many examples in diamond anvil cell research is really probably the place where Raman has had the broadest impact, is to be able to do soft X-ray spectroscopy inside a diamond anvil cell. There's also a little bit of work out there on Raman scattering on batteries and battery materials, which is something I think could be more important in the future. Seema, what am I leaving out? You've been in the field much more actively than I have lately.
Well, one important application is high pressure research, where the diamond anvil cells or similar are not permeable to softer X-rays, water research. Well, you mentioned many of these things. So catalysis or lithium-ion battery chemistry, things like this. So in many cases, the soft X-rays are stopped already at the very beginning of the sample cell and on the surface and cannot penetrate inside in the where the actual reaction takes place. So that's the main point. High pressure.
Okay. All right. Shall I continue now, Simo?
Yep.
All right. So this is today's paper is this PhysRev letter from 2010. And what we're doing here is we're doing a head-to-head comparison of the X-ray Raman scattering from nitrogen gas and electron energy loss spectroscopy, or EELS, from the same nitrogen gas. So, right, we have this expression for the double differential cross section that we saw before, and we've generalized a bit here. The S of Q omega in the limit of weak interaction between the probe quantum and the scatterer. This S of Q omega should be the same whether you're inelastically scattering an electron off the nitrogen or inelastically scattering a hard X-ray off the nitrogen. The pre-factor is certainly different. Again, this is the Thomson cross-section with the polarization dependence, but no Q dependence if you're bouncing X-rays. But if you're bouncing electrons, then you're going to get the Rutherford cross-section. And you want to remember that this is going to go as 1 over momentum transfer to the 4th. All right, so this is the main figure from that paper, and I split it to try to make it a little bit bigger. The horizontal axis is energy loss. The vertical is the magnitude of S of Q omega. And you can see we've labeled in atomic units different momentum transfers. So here at 0.4 AUs should be pretty close to a dipole limit. And the solid line, which is the eels, and the dotted symbols, which is the X-ray measurement, are in pretty good agreement. Maybe something's a little bit quantitatively not in agreement, but it's not bad. We go to 0.8 AUs, and they're still sort of in agreement, but you can see the relative amplitudes of features have kind of flip-flopped in some cases. And as we keep going up, you start to see there's differences between the eels and the IXS. For example, this feature, which had been strongly present in the IXS at 0.8 AU momentum transfer, has just about disappeared in the IXS at 2.8, but it's still there in the eels. And as you keep looking at these spectra, the same thing kind of happens. Is features appear and then disappear in the IXS, but they appear in the eels and then they stay there. They don't go away. So something is clearly different about the two techniques when you get out of the dipole limit. So if we go and look a little bit more at the underlying theory, we'd say, all right, here's S of Q omega. We have this matrix element with the e to the I q dot r in it. We can do a usual expansion of the e to the I q dot r with Bessel functions and spherical harmonics. And then because we know about, orthogonal functions, we'd look at this and we know that JL of QR has a peak in it, which moves gradually to higher and higher values of the argument as L goes up. We would say, okay, we expect that features are going to turn on when QR is big enough for its delta L, the relevant delta L for a particular molecular excitation. When that Bessel function has a high amplitude for a given value of QR, then we'll see that excitation. But as QR gets bigger, as Q gets bigger, the Bessel function is going to come back down to 0 again. And so you expect to see selection rules turn on and then turn off as Q increases, exactly because of the functional dependence of the Bessel functions. And so that's what happens in the non-resonant inelastic scattering or the Raman scattering, but it's not what happens in eels, right? The features turn on, the selection rule becomes allowed, and then they stay on. So we started digging into the literature on electron scattering. And what we found was there had been a lot of work, even contemporary work 10 years ago, that was looking at E2E experiments. That is experiments where you do impact ionization in eels on a core level, and then ask, how is momentum and energy actually distributed between the two outgoing electrons? And the surprise that was found in that community is that the 3 electrons, typically their momentum vectors are not coplanar. And that's important because it means that the ion, or in this case the molecule, was taking up some recoil momentum out of the plane. And that could only happen if there was a second scattering event inside the molecule. So the first-born approximation says that you only have a single scattering process with well-defined initial and final states and no relevant intermediates. Second-born approximation, semi-classically, would say you have intramolecular multiple scattering with a relevant, potentially relevant intermediate state. And remember, I told you, pay attention to the fact that the Rutherford cross-section goes as 1 over Q to the 4th. So at high apparent Q, that is a high momentum transfer defined by your scattering geometry. It turns out for electrons, it's more probable to get a double intramolecular scattering event, 2 events with low momentum transfer, so that their 1 over Q to the 4th isn't so big. It's more likely to get that than to get a single scattering event at the apparent experimental Q because of this 1 over Q to the 4th. So this isn't a spurious double scattering from two places in a medium. It's intramolecular and fundamental. And in fact, we see exactly what you'd expect if the firstborn approximation was badly broken for electron scattering at high momentum transfer. Every selection rule is there. Every possible transition is there when you're at high momentum transfer. So it turned out that the Q-dependent low energy excitations in nitrogen had been heavily studied because nitrogen with a triple bond made it a real playground to challenge theory. And previously, theory and eels had always disagreed on the momentum transfer dependence for these features. So we did a follow-up paper that I won't talk about today that showed much better agreement with theory. And that could even have some relevance for astrophysical spectroscopy. All right, I'll stop here again. Simo, do we have questions?
Yes, we have a question from the nickname Falamgair.
That would be me.
And okay, you want to say it out loud?
Hey, Faisal.
Yep.
Yeah, just to introduce myself, I'm Faisal Alamgir from Georgia Tech. Jerry, this is a little bit off topic given what you're discussing, but I wanted to know if you could comment on the relative importance of instrument limited energy resolution. It's like delta E over E naught in doing, let's say, soft X-ray XANES, NEXAFS versus XRS, and the core whole lifetime limited energy resolution in both of these cases. I mean, I think I know the answers, but I'd like to kind of I like to make sure that we discuss it so that my cobwebs are kind of cleared out.
Okay, yeah, it's a very good question. So it's been hard to greatly improve the energy resolution in the non-resonant inelastic X-ray scattering.
Yeah.
With the Lyrics instrument, we could sometimes get a bit under volt, the Lyrics 1 instrument. At ESRF, I think for some measurements, they're below half a volt. Is that right, Simo?
We used to have half a volt energy resolution at ESRF with specific stress relieved cut crystals. So having mentioned this, actually, I mean, it's not difficult to go higher in energy resolution. The problem is that then you lose often in count rate, which is then counterproductive for certain features that one wants to look at with X-ray Raman. So one can find a compromise between the resolution and the intensity. That's maybe the key question. Technologically, it's possible to go to higher resolution as well.
Mm-hmm. Yeah, and to answer the other question, I think the intrinsic core hole broadening should be pretty similar, right, in both. Okay. Other questions?
Not at the moment.
Okay. Then I'll try to go, as we're late on time here already, my apologies. I'll try to go relatively fast through this historical diversion. So, of course, C.V. Raman won the Nobel Prize in 1930, and Compton, on the other hand, won the Nobel Prize in 1927. And so in Compton's 1927 Nobel lecture, of course, we have the inelastic scattering, and relativistic kinematics lead to these results for the wavelength shift as a function of scattering angle and the kinetic energy of the recoiling electron as a function of its takeoff angle. So quoting from the Nobel lecture, Compton says that some experiments performed during the last few years has shown secondary X-rays are of greater wavelength, meaning lower energy than the primary rays. It's too well known to require description. On the other hand, careful experiments to find a similar increase in wavelength of light diffusely scattered by liquids have failed to show any effect. So he's saying there's inelastic X-ray scattering, but there's no inelastic optical scattering. So if we look at reference 25, this is a paper from the Proceedings of National Academy from 1923, where Ross, who is at Stanford, used a green mercury line, bounced it off paraffin, put it into an optical spectrometer and said, I don't see anything. He also at the same time did an X-ray measurement with the molybdenum tube. First, he did an exposure on this film with just the molybdenum tube aimed right into his spectrometer and got his elastic line. And then he bounced the molybdenum off of the moly radiation off of paraffin. And he got this broad IXS band from the paraffin and a little weak elastic line there. But he said there's no such thing as optical wavelength Compton scattering. There's no optical inelastic scattering. You know, the funny thing about this is it's in modern days, we'd say the funny thing is that Compton doesn't mention anything about Raman's work, which started in 1922, and also doesn't discuss the possibility of inelastic scattering accompanied by an internal excitation. Of course, there weren't internet-based journals and databases and everything back then. So let's go on now to Raman's Nobel lecture. And so quoting from it, the investigations referred to were guided by classical EM theory, particularly Rayleigh and Einstein. Nevertheless, the possibility that the quantum nature of light can be important wasn't overlooked. And he says he elaborately discussed it in 1922, which was published at least a year before Compton on X-ray scattering. He then goes on to discuss several studies by his team that do see inelastic optical scattering. And these observations left little doubt the phenomena was really a species of light scattering analogous to the Compton effect. So then they pushed fine energy resolution using monochromatic light, and they found this. They found discrete lines. They found something that didn't look like Compton scattering. Instead, there had to be internal excitations of a molecule in order to explain this. So this idea of inelastic scattering with an internal excitation being called Raman kind of got stuck in the community early on. There was a series of relatively controversial articles in the 50s and 60s that claimed to see valence level contributions to inelastic X-ray scattering and called it Raman lines. But it really wasn't until the mostly the 1970s, I think, when, you know, there were a fair number of papers being published with lab spectrometers that showed data kind of like this, where they're looking at, oh gosh, what is this, 40 EVs. I actually have forgotten what element they were looking at here. 40 EVs, I have a suspicion that's beryllium, but we may have to look that up. And they have a big Compton background, and they have the Raman, which came to mean the inelastic scattering from the semi-core level, as opposed to the Compton, which is the inelastic scattering from the free or valence electrons. So the name stuck. Something I would love to have known is what personal discussions or correspondence Raman and Compton might have had through the years afterwards about the different light scattering and whatnot. But I apologize, I didn't have time to go looking for a PhD dissertation in history of science on either of these two scientists, which I think would have been fascinating. So that's what I wanted to discuss. Are there questions?
Well, I have a question.
Go ahead.
So, in the very beginning, you were considering the different channels of X-ray Raman depending on the momentum transfer that one can excite through different multipoles, right? So how about interference between these channels? Have you thought about that? Or
interference between the channels?
I mean, they are all inside the square, right? So
yeah.
I mean, if you have two comparable intensities from two different channels, could you see the mixing term, an interference term?
It's a really interesting question. Give me just a second to think about it. the reason why it seems, I mean, from what you say, it seems possible that the reason I'll be skeptical is that you're probably doing the trend. You're probably doing the transition between different final states. Right, because if your initial and final state are usually going to have a unique selection rule connecting them. And so you can have two different matrix elements, like you're saying, have the same energy transfer, but I'm not sure they're going to be actually to the same final state. Did that make sense? I'm thinking molecularly here, right? You can have degeneracies where you have two different molecular orbitals at the unoccupied molecular orbitals at the same energy.
Right. For a molecular orbital,
what do you think?
That would make sense. But maybe if you have a solid state system and then your states in the unoccupied states are not pure states, but they are also mixtures of different characters. I don't know. This is just
yeah, it's interesting. It's funny, as I was
question.
thinking, if you have something where you're saying, okay, it's a very plane wave state. Let's say you're at fairly high electron kinetic energy. You know, my intuition is
or
you
a
would
metal.
take the plane wave. Yeah, you would take the plane wave and say, okay, I'm going to break that down in a spherical approximation. And then again, the selection rules are only going to pick out one piece of that, and they'll pick out a different piece for different delta L's. And so then again, I'm not sure that you get interference in those situations. It would be a good thing to ask Josh Cass or John Rare or an appropriate theorist. It's an interesting idea. Have you seen it discussed before?
Actually not. It just popped into my mind right now.
Okay.
Good. Okay, we can continue. There's a comment that the conversation between Raman and Compton may be available from the Raman Research Institute at Bengaluru. They have the archives of Raman, right?
Ah, excellent. If someone happens to come across that before I'll put it on my to-do list. If someone happens to get to that before I do, please email it to me and I'll distribute it on the list, and maybe I'll edit the slides and put it in there also. I just know that I'm spending the rest of the day with my kids, so I can't promise to immediately look that up, but that's very useful. Thank you. Also, I'm going to make a PDF of these slides and post them someplace that will be linked from from this website, so that anyone who wants a PDF of these slides, for example, if you want to be able to grab a DOI of an article so you can do additional reading, you'll be able to grab it there.
Right.
Jerry, I noticed that you're recording this. So is the recording going to be available to all of us, or is it just
That's the hope. That's the hope. Yeah, it's the first time I've recorded in Zoom, and so I may have a bit of a learning curve, but
Okay.
The intent is to come up with a library of these talks.
Very good.
By the way, the material for Cohen was lithium. It has the KH of 60 electron
Lithium.
volts,
Okay.
and the beryllium would be 100.
Okay.
110,
thank you.
something like it.
Yeah, I wanted to mention Cohen, for those of you who might be from Argonne Labs, was actually Gabrielle Long. Cohen was her maiden name. So in her PhD work, she had done X-ray Raman scattering. All right. Then hearing no more questions, I'll remind you that please sign yourself up or sign your postdocs and students up to give one of these short presentations. If someone would like to volunteer to organize a theme around beamlines or any of these other topics or anything you find interesting, please do so. Let me know and we'll make sure we schedule it. And yeah, I wanted to thank everyone, and remember to stay healthy and to be kind to the people around you, because everyone is having difficult days sometimes. So that's what I wanted to say, and thank you for coming today.